Okay, here's part 4 of 15.1. We're going to try to finish off section 15.1 right now. We'll do example number 5 and 6. But before I do example number 5, I want you to look at this indefinite integral that I wrote here, 1 over x. I would like you to think about what you think the antiderivative of 1 over x is, or how you would do this problem. How many of you thought about taking this x and bringing it up to the top and making it x to the negative 1? But then if I go to apply my antiderivative power rule, doesn't power rule say that I add 1 to the exponent? And so if I added 1 to the exponent, then wouldn't I get x to the 0? And then doesn't power rule say with antiderivatives I divide by that new exponent? But wait a second, whoa. We can't ever divide by 0 in math. So that's not right. Something's wrong here. I can't use my power rule when it looks like that. Does anybody remember what the original function has to be in order for the derivative to be 1 over x? Maybe you did. It's natural log of x plus c. Remember that the derivative of natural log of x is 1 over x? And so as soon as I see that 1 over x, then I know that I can't use power rule anymore. I should never, ever be dividing by 0. That should be your red flag. But the antiderivative of 1 over x is really the natural log of x. Technically, there should be absolute values around that x because natural logs can never be negative. But the antiderivative of 1 over x is natural log of x plus c. So that's a new rule that we're going to do now. Anytime I see a x to the negative 1 or a 1 over x and I'm doing the antiderivative, please don't use your power rule. Make sure you remember that the antiderivative of 1 over x is really natural log of x plus c. Okay, so look at example number 5 with me. If I have 4 over x, you could think of this as just a number and bring that 4 out in front, leaving me with a 1 over x. Oh, and there should be my red flag. Oh, how about pink flag? My pink flag that the antiderivative of 1 over x is not power rule. It's really natural log of x. I have the 4 in the front. The antiderivative of 1 over x is natural log of x plus c. Okay? All right, look at b then. You should be able to recognize that this is a negative 5 times a 1 over x. And the antiderivative of 1 over x is natural log. So you should have a negative 5 times the natural log of x. Oh, and look at this rule. That was our rule from before where we had an e to the kx. Do you remember what the antiderivative rule is there? Well, it's e to the kx over that k. So I have here negative 5 natural log of x. I have the minus sign here. That was from the 2 here that I brought up here. I have e to the negative 2x plus c. I know that this exponent is negative, but I'm okay with you leaving it the way it is for right now. So I have negative 5 natural log of x minus e to the negative 2x over 2 plus c. So using a couple different rules in one on that one. All right, the last little thing that we're going to do in section 15.1 is what we call initial conditions or particular solutions. All the antiderivatives we've done so far have been what we call general solutions because they've had that plus c in the back. There's just been this constant of integration, but we weren't sure what it was. Well, now we're going to actually figure out an exact function. We're going to figure out what that c is. So it says here an equation that involves the derivative of a function is called a differential equation. And so if I ask you to find me the antiderivative, big F, if the derivative is 3x squared minus 1, then we can use our power rule and we can say that if this is my derivative, then my antiderivative would have been x cubed minus x plus c. But what if I told you that the original function, big F, went through the point 2, 4? We're going to call that my initial condition. What that means is that x is 2 and y is 4. Well, since I know that x is 2 at that particular moment and y is 4 at that particular moment, can I take that information and plug it into my function? So I know that, get blue here, that y is 4, x is 2, And what does that help me do? Well, it looks like that helps me solve for C. So I can finish this problem off. I can solve for C and end up getting C is -2. So now I not only have a general function with that plus C, this x cubed minus x plus C, well, now I have a particular solution. I have an exact solution because now I know what C is. So I can tell you if big F goes through the point 2, 4, and the derivative is 3x squared minus 1, well, big F has to be the equation x cubed minus x minus 2 because that's what my C was. So now I not only have a general solution, I have a particular solution. I have the exact original function. Let me show you another example of when that could possibly be used. Let's do a cost problem. So example number 6 says, suppose a publishing company has found that the marginal cost at a level of production of X thousand books is given by this equation. So this is my marginal cost, or the derivative of cost, or the rate at which the cost is changing, right? If this is the rate at which the cost is changing, and it says here, and that a fixed cost, the cost before books can be produced, is $25,000. So at the beginning, in order to start up your business, you have to pay some money for equipment and stuff like that. What that's saying is that before I make any books, the cost is already $25,000 for me. Okay, so I know the derivative, the rate at which the cost is changing. I know my initial condition. When X is 0, it's going to cost me $25,000. The question is asking us to find the actual cost function. I know the derivative, but I want to find the original cost. I know the rate at which cost is changing, but maybe I want to know what the actual cost is. So I need to go backwards and do an antiderivative. So I actually want to find the antiderivative, or I want to integrate my derivative, the 50 over square root of x with respect to x. I saw that square root of x, and so I changed that into a 1/2. I saw that it was on the denominator, and so I didn't want to have to do a quotient rule because there is no quotient rule, so I brought it up to the top. And so now I'm integrating 50x to the -1/2. I'm now going to use my power rule. I'm going to add 1 to the exponent and divide by that new exponent. I'm going to simplify it a little bit, and I end up getting that the cost function is 100x to the 1/2 plus c. But I would never be able to figure out what the cost is because I have too many missing variables. I don't know how many I've sold. I don't know what this constant of integration is, so I really can't figure out what my cost is. But if I can figure out what that constant of integration is, well, then I could be able to figure out what the cost is anytime I produce a certain number of books. Books, was it? Oh yeah, books. Okay. And so did we have an initial condition? Did they tell me something else about the situation that I can plug in some values? Well, yeah, didn't it tell me that when I started off, before I produced any amount of books, I had a fixed cost of $25,000? So really what that means, when X is 0, my cost is already $25,000. So can I plug in that initial condition into this equation, and that'll help me find what my C is, what my constant of integration is. So now I know that my constant of integration is $25,000, and I can actually say then that my cost function, the cost to produce any amount of books, would be 100 times the square root of x, or x to the 1/2, plus $25,000. So when I ask you to figure out what the cost is after producing 2,000 books, can I plug in a 2 there? Or 3,000 books, I can plug in a 3 there, and you should be able to figure out the cost at any moment. We know the rate at which the cost is changing up here, and now we know the actual cost to produce any amount of books. So I can use my antiderivative and my initial conditions to find an exact solution. Okay? All right, that was the end.